I will speak a little bit about the work that we've been doing in the modeling center for the last 9 months or so, work that started off in producing forecasts, short-term forecasts for MSF, in how many beds they would need, in looking 1 or 2 weeks in advance, and something that has then turned into much more detailed forecasts for all of West Africa or the affected regions in West Africa, and the production of weekly reports, which some of you may have seen, and I'll mention these again in the end. And I should say that really I'm standing in for Anton Camancho, who's been leading a lot of this work, but who's on holiday, which gave me the chance for a trip to Oslo. Okay, so where are we at the moment? So this is data as of 2 days ago, as of Sunday, from Sierra Leone. This is just looking at different regions in Sierra Leone. You have the national picture in the corner there, and then these are the different districts of Sierra Leone where there's been Ebola transmission. And if you look at this and put yourself into a position at any point in time, say here in Bo, and you're trying to make a forecast, then that actually looks like a pretty difficult task, because things are going up and down, and there's a lot of heterogeneity in there, and there might be certain events at certain times that cause spikes or decreases at any given time. So in principle, you're faced with a pretty arduous task in trying to make forecasts here. Now, what we essentially did, and I'll go a little bit into detail in the next couple of slides into what we did in detail, but what we essentially did was at any point in time, look a bit back and just see what is the trend, okay? So that's the simplest thing you can do. So if you're here, and you saw maybe 2 weeks ago it was like this, and then next week like this, you see, okay, so there's a decreasing trend. And then next week, okay, so next week you're here, so then you say, okay, there's an increasing trend. So your forecasts at this point would be that it's going down, at that point would be that it's going up. That's essentially what we're doing. Now, what we've been doing is ever so slightly more sophisticated, because what we can do is we can take into account what we know about transmission of Ebola. So we know things like the incubation period. We have a rough idea of what the incubation period is, and we know how long people are infectious, and we can actually put this and the case fatality ratio into a dynamic model of transmission, and then filter what you saw on the previous slide, filter the data through the lens of a model like this. And so, for example, what you see in transmission really is a reflection of, or what you see in cases, is a reflection of the intensity of transmission as at least 2 weeks back, or around 2 weeks back, because you have this incubation period and infectious period. So taking this into account, we can maybe get a slightly more sophisticated, better understanding of what's going on, and make predictions on the basis of that. And then we have a transmission rate here. So this is how people, from being susceptible, become incubating, and then go on to being infectious and recovered. But this here, so there's an unknown transmission rate here, and there's a key here. I'll come back to this in a second. So this will be dependent on time, and I'll briefly speak about how this is depending on time. Okay, so this is what we know, and this is what we can actually put in. Now, there's a lot of stuff that we don't know. On the next slide. Here we go. Okay. So there's a lot of things that drive, I mentioned it on the earlier slide, a lot of things that drive this heterogeneity that we see, and these spikes and this going up and down, that actually, at least at the time, in real time, usually we don't have this information. We may have it afterwards, but in real time we don't know how much transmission is happening in the community, in the hospitals. Usually we don't have the data that resolve these things. We don't know how much transmission happens in funerals. And then crucially, there'll be changes in behavior happening, both in response to perhaps deaths that happen in the community, but also the international intervention, which leads me to the next point, which is also through expansion of bed capacity, but also anthropological interventions, and so on and so forth. So we don't know all of this. And so what we do is we don't even try to take all these things into account in our model. Instead, we do something, we basically, so I mentioned earlier the transmission rate, we let it vary over time, and we let it vary over time randomly. So this is what you see here, this equation, don't worry if it doesn't make sense to you, but basically you have a stochastic process here. So it's basically borrowing an idea from the way financial markets are modeled, and this is based on physics. So there's Brownian motion in here. But so the crucial thing to understand here is that this transmission rate, we allow it to go up and down and change, and then we look at how much we have to allow it to change in order to be able to describe the outbreak. And this how much we allow it to change is called the volatility. Okay, so this is a term which is usually used in modeling financial systems, but it's basically telling you how much is something varying around a more common or a more general trend. Where here the trend we assume there to be no trend, so it's just we assume that it's flat, but then there's a volatility around this transmission rate. Okay, I promise that's the only equation you'll ever see in this talk. Okay, so what we do is then we have this model, and then we have this transmission rate that we allow to stochastically vary, and then we fit it to the data. So we fit three parameters. Crucially, this volatility. So how much do we have to allow the transmission rate to be flexible and change over time in order to describe the outbreak? And then also two other parameters, initial number of infectious and overdispersion, not particularly important in this context. And then use some method that allows us to, once we have done this, so we fit all these parameters, and then we can use this to filter out likely future trajectories using this method here. But again, I'm not going to talk much about methods. Okay, so the rest of the talk, I'll show you the actual forecast and how well we've done. Okay, so this is one typical situation. So this is from Sierra Leone, 1, 2, 3, 4, 5, 6 weeks of data, and then so this is our fitted model trajectory, and the fitted model trajectory corresponds to a behavior of the reproduction number. Okay, so I said earlier, I talked about transmission rate. Here I translate the transmission rate into something that's a bit more tangible epidemiologically, which we call the reproduction number, which is the number of secondary cases that each case generates. And crucially, if that's greater than 1, you have an increasing epidemic. If it's smaller than 1, you have a decreasing epidemic. So if every case leads to more than one subsequent case, you have the chain reaction of cases and exponential expansion. Okay, so zooming out a bit, so this is about 6 weeks here. Zooming out a bit, so if we want to make a forecast on the basis of that, well, what we can do is we look at the most current value of the reproduction number in between September and October, and then we assume that it doesn't change anymore. Okay, so that gives us one trajectory, and we can extrapolate that forward as long as we want. And some of you may remember that last summer, there was one particularly frequently cited CDC projection that there'll be millions. That there might be. It was an upper limit that was then taken as a headline figure. But there might be more than 1 million cases by December, which obviously did not happen. But that is based on an assumption that nothing changes, because, as I said earlier, there's all these things that could change community transmission behavior and all of these things. But we don't know how much that's going to happen. So one approach would be to just say, okay, we assume that everything stays the same, so then that is what's going to happen. If there's no intervention, no behavioral change, that's what's going to happen. Okay, but then if we now take into account variability here, and I said earlier about the stochasticity, we get confidence intervals around that. Okay, so there's 20% intervals, 30, 40, and so on and so forth. So in fact, if you go all the way to 90, it could be pretty much everywhere. So again, remember what we're doing here. So we have 6 data points. We have a model that we fit to the 6 data points. We take into account the full variation of the variation in the reproduction number and also the range of reproduction numbers or transmission rates that would conceivably describe this data. And then we assume that, so then we get this range of reproduction numbers here. And then if we extrapolate that forward, we get something like this. So arguably, from the information that we can get from the data here in September, taking into account variation that has happened up to then, in January, anything could happen. Okay, so what we've been doing because of this is focus much more on short-term forecasts, and I'll get to how reliable these short-term forecasts were. Just to say, so this was between September and October. This is what actually happened. So the median forecast is here. This is the interquartile, 50%. So we had 50% confidence that the trajectory would be between those two, which it actually was, and then 95% confidence that was between those wide regions. Okay. This is what we did every week. So we would start, so this is going back to the first 3 of those 6 data points. So we'd go here, and then we'd project 3 weeks forward, 2 weeks in this case. Okay, so we look at what has happened so far, take all the range of reproduction numbers, and extrapolate it forward. And then in all the pictures I show you, there's, I don't know if you can see this dashed line is the median, then these two lines is interquartile, so 50% confidence between these, and then 95% confidence in the outer ones. Okay, so okay, next data point was here. Okay, so it's outside the 50% confidence interval, and then next week we refit and we do this kind of prediction again. Okay, do this again, do this again. Okay, this looks quite nicely in the middle or in the quartile range. Okay, so then this one happened. And what happened here is that between these two data points, there was a 3-day shutdown in Sierra Leone where there was an active case-finding campaign. And so presumably, or conceivably, this data point is a reflection of that active case-finding campaign, and there was a change in reporting here, and probably because of this data point was lower. Okay, but then we refit and do this, project this forward, go forward in time, so we're now in November, December, and then we get to this one here. Okay, for this one we didn't have an explanation. So something happened there, and I mentioned all the factors before that we're not taking into account. So this one was very much outside our projection, and for whatever reason, we don't know. Okay, but then again, we can refit, keep going, and the same thing again here happens, so there's a drop here, which we couldn't really explain. Okay, and since then, epidemic's been declining, and so this is based on confirmed cases. Now it's actually relatively stable and a bit higher again. This is the complete picture. So this is looking every time at just a 1 week ahead forecast and then seeing where that data point fit in. So it's always from that point forward. So judge for yourself whether we did well or not in the forecasts. Obviously, we can't work magic with this, and we can't forecast the unforecastable, or we can't forecast unexpected events. But again, we try to do what is a reasonable forecast on the basis of the data that we had available. Perhaps to illustrate, or to be a bit more rigorous about how well we did with the forecasts, we tried to kind of graphically illustrate or put that into a different form, the previous slide, and make it a bit more rigorous. So I told you that we had these credible intervals or confidence intervals, and you would expect that, for example, 50% of your observations should lie within the 50% confidence interval, and all of your observations should be within the 100% confidence interval. If you look at how we actually did, this is 1 week forecast, so it's actually relatively close. If anything, we're slightly overestimating variability or underestimating the precision. So we actually were the data points laid within the 50% confidence interval more than 50% of the time. But generally, with a 1 week forecast, arguably forecasting for 1 week is not very difficult, but with a 1 week forecast, we did relatively well. If you look at longer, 2, 3, 4 weeks, then we diverge further away from that line, and that brings me back to the point I made earlier that forecasting very far in advance with something that's as variable as this epidemic has proven to be, with a lot of heterogeneity even within countries and even within districts, it's very difficult to make forecasts so widely. Okay. Now, I promised I would say briefly where we are at the moment, and this is how I'll conclude. So we have this, I said we have been producing weekly reports, so this is our website, and there are these situation reports and projections, and if you go there, so there's latest weekly, so we summarize all the data for Liberia, Sierra Leone, and Guinea, and then we also show forecasts, so these model fits and forecasts for the next week and next 3 weeks. And we've been doing this weekly for all the districts that had transmission in the 3 countries. So currently this is Guinea, so Guinea is a bit of a concern. This is again data as of Sunday. So in Guinea, cases have been going down, but now there's actually been a quite drastic increase in the last week after sort of relatively stable bit of wiggling around here. We'll have to see whether there'll be a regression to the mean or whether there's genuine increase here. This is blue as confirmed cases and brown as probable. And then, but we also look at a finer detail. So this is again Guinea. This is now 1 week out of date. These were the forecasts from last week, and we're updating the forecasts as I speak. But so we do these model fits and then do these projections into what we think will happen. And now, obviously, Conakry and Koya is where the ring vaccination trial will take place, and we're helping with that. And there's still sustained transmission going on there, And then for a career is a particular concern at the moment. And with that, I conclude, and thank you for your attention, and thank all the people that have worked on this and the funders.
Thanks very much, Sebastian. We've got time for a few questions, if there are any. While we're waiting for the first question, maybe I'll ask just, have you any idea of how useful these projections have been to those to whom you've been giving them?
Yes. So, well, I think the projections. Okay, there's two answers to this. One is they have been appreciated, and I think there has been particularly even just visualizing the data, but also the projections. I think there's been a bit of a disconnect between people on the ground and people analyzing the data, and there seems to have been a desire by people working in West Africa to see what is going on around them, and there wasn't always a good synthesis of information of what's going on in different districts. So we had a lot of appreciation from there, and in that. That's the one side, and the other one I think is, so we're involved in two vaccine trials. One, the ring vaccination trial, and also another one where we actually these updated forecasts are used to inform the vaccine trials and to inform their design. So I think in that sense they have been in one sense they have been useful. They have also, I think, initially been useful for MSF in planning. They're obviously just one part of many things that contribute into their planning, but I think they have been appreciated as one part and as a good visualization of what is going on and what might be expected in the short-term future.
Thank you. Yeah.
Yes, okay. Question about the quality of your data sources. I've worked a bit with the information system in Liberia, and at least back when the outbreak first occurred, I wouldn't have put a lot of confidence in their ability to report very accurately on the morbidity figures or what have you. So just what it was like, how you determine the validity of the sources that are coming in, what is the source of information behind some of these? Thanks.
Okay, so what we now use, it has changed a bit over time. What we now use is a combination of the WHO patient database and CITREP data. So we're modeling reported cases. We're not taking into account underreporting, so we're modeling an epidemic of reported cases. And yeah, I think the forecasts and the fits can only be as good as the quality of the data, and that is an issue. And I mentioned earlier in that even if that the changes in reporting are tampering with our forecasts, basically. So we use since WHO have published their aggregate figures from the patient database. We use this, so this is confirmed Ebola cases as reported by WHO. This tends to be not very up to date. So the last 3 or 4 weeks are always they sort of catch up in reporting the cases, and so for that we use the information from the CITREPs. So this is what's reported to the Ministry of Health, and then published by the Ministries of Health.
One last question.
Thank you very much. I thought this was very interesting. And now, are you planning, since you had a lot of the unknowns, and in some of the countries and some of the places, you will know the unknowns when things are over. So are you then planning to go back and model given unknown information for A and B and C and D and all these kind of things, and then see which are the ones that actually are the critical unknowns?
Yes.
To do this.
Yes, and in fact we're doing this already. So in Liberia, where the outbreak is over, we have, for example, very good information from Lofa County, where MSF has been heavily involved, and we know about the health promotion campaigns they ran at different times. So the simplest thing we can do is look at a model where we have the reproduction number varying, as I said, and just look at whether the drop in reproduction number corresponds to any particular intervention. Now, the problem there is that a lot of stuff has happened at the same time, and different agencies came in. And I think what we'll have to do, and what we will do once all of this is hopefully over, is compare across different regions what changes in the transmission rate corresponded with, and then perhaps or hopefully come to conclusions as to what actually worked and what actually made a change.
Great. Thank you very much indeed.
Thanks.